All right, guys, so we're still in chapter 10.4, talking about polar graphs. Yesterday, we just kind of learned about polar equations and how to graph polar coordinates, how to switch from polar coordinates to rectangular and the relationship between those. Today, we're going to learn how to sketch these graphs by hand. And I will say on the BC test, you're probably not going to have to sketch an entire polar curve by hand, but it's important to know how to do that because you'll be given a graph and you'll be asked to find the area of a portion of the graph, and you'll need to know how to figure out where, what are the bounds of integration? So what are the polar coordinates that make up whatever portion of the graph you're looking at? So that'll make a little more sense in the next few days. So it is worth our time to graph by hand. If we skipped this, we probably wouldn't have a very good understanding of how to do these area problems that we're going to do for calculus. So with all of that said, there are two main ways to sketch a graph by hand. The first way I'm going to show you is by actually graphing, like doing the sign graph. Go back to your pre-calc days, sketching the sign graph, and then using the coordinates on your graph to plot onto the polar curve. Some people prefer that method. I kind of switch back and forth. I like the visual. Another thing is just to make a table of values, plug them into R and plot them that way. So I want to show both. I'll show one of each so that you can kind of see the relationship. All right, so let's get the sine curve. Couple of things to review here. First of all, you need to know what a sine curve looks like in general, not transformed. There's a sine curve, right? You need to know the period of the sine curve. So how long does it take to go through that one cycle? If this is 2 theta, the period is 2 pi divided by b. The period is pi. And then to generate this graph, remember you cut that in half, cut that in half, put another halfway point in there. I want to label all of these because when I'm plotting polar coordinates, I'm plotting r theta. So I need to know which angle am I facing and how many units am I walking forward or backward. So this is a -4 sine graph, and then it goes through. So I always have to sketch kind of the ghost points for myself. So like I'm going to call this -4, and that's 4. So before I shift it up 2, the graph would start at 0, 0, and then go down to -4, 0, 4, 0. I'm not going to sketch that in yet because I'm supposed to shift it up 2 units. So this point that was at 0, 0 is really at 2. This is at -2. 2, 4 goes up to 6. And then at pi you're at 2. So I'm going to sketch that in. That's just one period. I might have to do more. And I'm going to make a couple of notes here. I'll also kind of need to know, like, when does the graph hit 0? So there's a 0 and there's a 0. I don't necessarily have to find those points just to graph the thing. If I was interested in what those angles are, I would set the polar equation equal to 0 and solve for theta. All right, so armed with this information, I'm going to start at the beginning. Remember, you face the angle and walk out that many units. So face 0 radians and walk forward 2 units. There's the first point. These graphs always kind of spiral counterclockwise, so you'll see what I mean when we connect the next points. Then the graph hits 0. The angle doesn't matter. It doesn't matter what angle you face if you're walking out 0 units, right? So the first portion of this graph is a smooth curve that connects these 2 points. And then face pi over 4. Now pi over 4, remember, is not marked on this little grid. So I am going to draw them in though. So this is pi over 6, pi over 4, pi over 3. Okay, so face pi over 4, and it's -2. So walk backward 2 units like that. So I don't love to draw the spiral as I go because I can already tell I made that arch a little bit too much. Basically, here's what's happening so far. We have like this going on. Okay, and then we hit 0 again. So come back to the pole right there. And then I'm at pi over 2, go forward 2 units. Face pi over 2 and go forward 2 units. So now you're spiraling kind of this way. And then face 3 pi over 4 and go forward 6 units. This might be off our grid a bit. 1, 2, 3, 4, 5. Yeah, just one ring short. So put 6 out there. And so that means that we connect out here. And then the next point is face pi and go forward 2 units. So a polar graph is not complete until you get back to your starting point. So since this is a sine of 2 theta graph, that's kind of my hint of like, you're going to have to go through 2 periods to be able to get the full curve. So you could extend your graph out. Although the points are going to kind of fall in the same pattern, right? So you could either sketch it out again, like go out to 2 pi and figure out all of your points, right? But really you're just using the same angles in the next quadrant. Let's see. So after pi is 5 pi over 4, 3 pi over 2, and then what's the pi over 4 angle in quadrant 4? That's 7 pi over 4. So then your next point would be at 5 pi over 4, you're at -2. And then next one is 2, and then we hit 6 again, and then we end at 2. All right, so what happens here? So we were right here, right? And then we hit 0. So we hit 0, so plot a point, come back to the pole. And then what happens? Then we are facing 5 pi over 4, and we're going backward 2 units. So face 5 pi over 4 this way, but go back 1, 2. So we're here, and that kind of makes sense. It goes with the flow of everything. And then we hit 0 again. Oh, that pedal's looking rough, but it's fine. They're kind of hard to sketch for me anyway. Okay, so I'm there. Hit that 0. Face 3 pi over 2, and go forward 2 units. You can see some symmetry happening. Like I can kind of guess what the shape's going to look like, right? But if I follow my graph, 7 pi over 4, out 6 units. Give me this thing. And then face 2 pi and go out 2 units. So it took 2 full periods because I had a 2 theta angle there for me to complete this polar graph. So that's another thing that we'll need to be able to figure out, like where's the starting and stopping point of the graph. All right, what's another way to do this? You don't have to sketch the graph. If you notice the angles that I was using, the important angles were the zeros, pi over 2s, and pi's, 2 pi's, right? And then also because of this 2 theta, the pi over 4s were important because if you plug pi over 4 into sine of 2 theta, sine of 2 times pi over 4 becomes sine of pi over 2, right? And so for any of these, it's like sine of pi over 2 or sine of 3 pi over 2 or sine of 5 pi over 2 or 7 pi over 2. Those will all give me ones or negative ones. And so those are points that are easy to plot and work in here. So I'm not going to go back and make a table for this one, but I'll make a table for the next one. So you could also make a table of values. Let's look at 2 cosine of 3 theta. Now, if I'm going to make a table of values, remember the important angles are the zeros and the pi over 2s and the pi's. So a thing to think about is, okay, well, 3 theta equaling 0 is not a thing I need to check on. But what about when does 3 theta equal pi over 2? That would be when I divide by 3. All the pi over 6 angles. So I need to make sure that if I'm just generating a table of points, that I should include pi over 6 angles. And when is 3 theta equal to pi? Because that's another important mark. Well, I should include pi over 3 angles as well then, if I'm going to make this table. And so you don't really have to check beyond that, because if you say, when does 3 theta equal 0, theta equals 0, of course I'll plug that in. And I will still plug in like just pi itself and 2 pi and things like that. All right, so let's make this table. I'm not sure if I erased it or not on yours. You might already have a table going this way. It doesn't really matter. You always start at 0, so plug in 0. And then the cosine of 0 is 1. So 10 1 is 2. So I face 0 and I go out 2 units. And then remember, we said we need to include pi over 6 angles and pi over 3 angles. I'm not going to do pi over 4 angles because those would give me weird radicals. Those are not nice integer numbers when I multiply by 3. So pi over 6 is my next angle. 2 times, I'm going to write this in the cosine so I don't screw it up. The cosine of 3 times pi over 6 is really pi over 2, and the cosine of pi over 2 is 0. So we are back at the pole. So far we've got that happening. And then we also need a pi over 3 angle. 2 cosine of 3 pi over 3 is just pi. That's 2 times -1. Face pi over 3, which remember is this guy, pi over 3, but go backward 2 units. So 1, 2, so you're down here. And again, it should kind of seem like, oh yeah, that flows nicely in that counterclockwise pattern. All right, and then I'm picturing where I am in the unit circle, by the way. So now I'm at the top. I'm at pi over 2. You can kind of let your polar graph guide you as well. So I plug pi over 2 into this, I get 2 cosine of 3 pi over 2. Cosine of 3 pi over 2 is 0. So we're back at the pole. So kind of something like that. It is so hard for me to like sketch these as I go. They're not great. Okay, and then where are we? Next value would be 2 pi over 3. That becomes cosine of just 2 pi when you multiply by 3. Cosine of 2 pi is 1, so 2 times 1 is 2. So at 2 pi over 3, walk forward 2 units. All right, and then next angle is a pi over 6. 5 pi over 6. 2 cosine of, when you multiply that by 3, you've got 5 pi over 2, right? Because 3 over 6. Now you're back to 0. So again, maybe you can guess what it's going to look like, but it's kind of good to verify here. What's the next part? Now I'm down here at pi. So 2 cosine of 3 pi is 2 times -1, -2. Face pi, but go backward 2 units, and you're back where you started. So when we had a 3 theta here, it only took us from 0 to pi to complete the whole thing. All right, so like I said, where are we headed with this? We're headed with questions that say like, well, find the area of this polar curve? And I'll need to know, can I find the area of one petal and then multiply that by 3? Or, how do we go about that? So that's in the future. Another thing we need to know, this is more algebra based now. How do we find the slope if we have a polar curve? So in the last section, when we had parametrics, remember dy dx was dy dt over dx dt. Now we have dy dx is dy d theta over dx d theta. Right? dy d theta over dx d theta. Or y prime of theta over x prime of theta. Now, remember, we have ways to get x and y. X is r times the cosine of theta, and y is r times the sine of theta. And remember, r is some sort of function. It's an equation, right? It's not a constant. So when we say that it's y prime of theta, taking the derivative of y means I have to do a product rule. So it's the first function times the derivative of the second plus the second function times the derivative of the first. We'll just call that r prime. Remember, r is in terms of theta, so there's no extra like dr d theta. And then what about x prime? Same idea. It's the first function times the derivative of the second plus the second function times the derivative of the first. Now I'm going to rearrange this formula so it's in something that's easier to remember. It is definitely going to make your life easier to memorize this formula for dy dx when things are in terms of slope, so that you don't have to, otherwise you have to drive this little thing every single time. So I start with the r primes in front, r prime sine of theta plus r cosine theta. And then here, r prime cosine theta minus r sine theta. The primes go first. I kind of think of it, I don't know why I have this in my head. This is not equivalent at all, but I try to remember it as like tangent over cotangent, because like sine and then cosine in my head is like tangent. cosine minus sine in my head is like cotangent. That's not right, but that's just how I remember it. So anyway, memorize this thing so that when you're asked to find dy dx, you can just jump right into it. Now, if we're finding horizontal and vertical tangents, this is important for the AP test. You need to check when, for a horizontal tangent, that's when your numerator is equal to 0, right, of dy dx. In other words, that's when dy d theta equals 0, the y prime equals 0, but also we have to make sure that dx d theta, the denominator, is not equal to 0. Because if you get 0 over 0, that's one of those indeterminate forms. Vertical tangents are the opposite. When dx d theta does equal 0, the denominator equals 0, but we can't have dy d theta equaling 0. So when you're asked to, there aren't directions here, but the directions are find point, let's take this in, find points of H and V tangency. So to start this, I don't really want to start by putting together the dy dx. It would be easier for most of the problems to separately find dy and then separately find dx and figure out when is dy equal to 0, when is dx equal to 0, and then tackle the idea of, okay, so where are the horizontal and vertical tangents? So let's start there, and let's just start with x. So x is equal to r times cosine theta. And r is sine theta. So x is equal to sine theta cosine theta. And then x prime, this needs a product rule, is the first function times the derivative of the second, plus the second function times the derivative of the first. And to switch the order around a bit, that's cosine squared theta minus sine squared theta. All right. And now there are some formulas, like the double angle formulas and stuff, that I don't really have them memorized. So if you want to memorize them, you can. I think this is cosine of 2 theta. Sometimes it makes solving easier. But I prefer to work with, I'm trying to figure out when this is 0. So I prefer to work with those Pythagorean identities and just like sub in. I'm just going to sub in for cosine squared, for example. Cosine squared is 1 minus sine squared theta minus this other sine squared theta. Like I don't want to have cosines and sines when I'm trying to solve for something. So I'll just use that substitution. And in my brain, that works for me. Okay, so what are we getting at? I'm kind of running out of room here. I have a pretty good equation for x prime where I can go ahead and set it equal to 0. And so let's see. This will be 1/2, but then I square root both sides to get sine theta. 1 over radical 2, so radical 2 over 2 unsimplified. So all of the, and this is plus or minus, so all of the angles when sine is 1 over radical 2 are the pi over 4 angles. So x prime is equal to 0 at pi over 4. We're on 0 to pi. So at pi over 4 and 3 pi over 4, but I don't have to go beyond that because we're restricted here. Otherwise, I would go beyond it for full 2 pi. Okay, so I just put a pin in that for a minute, and then I need to go do the same thing for y. So y is equal to r sine theta, and that's equal to, remember, r is sine, so that's just equal to sine squared theta. That derivative is going to be a lot easier to find. Y prime is power rule first, 2 sine theta, and then chain rule, cosine theta. And again, I want to say that's one of those double angle identities, but honestly, I would just be saying, well, when is this equal to 0? I don't need to switch out an identity. It's just y prime is equal to 0 when either sine theta is equal to 0 or cosine theta is equal to 0. So on the interval 0 to pi, sine theta is equal to 0 at 0 and at pi, but pi is not included. And then cosine of theta is equal to 0 at pi over 2. And 3 pi over 2, but that's not in the interval. Okay, so now I double check these. We don't have any angles in common, so there is no point for which dx and dy d theta are 0 at the same time. So horizontal tangents are when dy d theta equals 0, right? But not dx d theta. So that would be at theta equals 0 and pi over 2. How do I get the points of horizontal and vertical tangency? Remember, points are r theta. So r is sine theta. So sine 0 is 0, and the angle is 0. Sine of pi over 2 is 1, and the angle is pi over 2. So I should probably write this in here. How am I getting r? I'm doing sine theta, and the angle just goes in. So these are points of horizontal tangency. And then for vertical tangency, I didn't color code these very well. That's when dx d theta, is equal to 0, but dy d theta is not equal to 0. We don't have to worry about that. Still plugging into r equals sine theta. So sine of pi over 4 is radical 2 over 2, and the angle is pi over 4. Sine of 3 pi over 4 is also positive radical 2 over 2. So if we were to graph this, polar curve, we should find horizontal tangents at the pole and at pi over 2, 1. R equals sine theta, by the way, is a circle. It's kind of a good thing to know. It's a circle, if you were to graph it, that looks like this. So this makes sense. We have horizontal tangents here and here. We have vertical tangents on the sides, I guess I'll call them. That must be the pi over 4 points that we would plot. Okay, it's a lot of work for one problem, I agree. There's no restriction on here. I'm going to go ahead and distribute the 2 through. I don't know if that makes it easier or not. That's just what I'm going to do for this one. We're going to go through the same process. So x equals r times cosine theta. So 2 minus 2 cosine theta times cosine theta. So x equals 2 cosine theta minus 2 cosine squared theta. I'm choosing to distribute it because that gets me out of having to do a product rule. So x prime is negative 2 sine theta, and then minus our rule for it, so minus 4 cosine theta, and then the chain rule says to make that a negative sine theta, so I'm going to plus, put my sine theta out here. Okay, and then I'm trying to figure out when this equals 0, so I'm going to use some factoring here. I'm noticing a GCF of either 2 or negative 2, it doesn't matter. I'll take out a negative theta sine theta. So that would become 1 minus 2 cosine theta. In its factored form, I can solve this equation. So sine theta equals 0 when theta equals, we don't have any restrictions here. So I'm going to go one full circle. So 0 and pi, and 2 pi, but I'm not worried about that unless I need it. And then theta equals, cosine theta equals 1/2 is what I'm trying to solve. So that happens at pi over 3, and it's positive 1/2, right? So you need the quadrant for pi over 3 angle, which is 5 pi over 3. That's everywhere that x prime is equal to 0. I'm not figuring out horizontal and vertical tangents yet. Now I need to go do y. So y is equal to r times sine theta. So 2 sine theta minus 2 cosine theta sine theta. And y prime is 2 cosine theta. We have a product rule here. Now, when I do product rule and there's subtraction, I consider the first function to be negative 2 cosine theta so that I don't have to bother with parentheses. So that's my first function. And then the derivative of sine is cosine, so squared. And then it's plus, the second function is sine theta. And then the derivative of the second function, I'm taking the derivative of negative 2 cosine theta. So that would be positive 2 sine theta, because it would be negative 2 times negative sine theta. So as long as you do that, then parentheses are not needed. So y prime is looking like 2 cosine theta minus 2 cosine squared theta plus 2 sine squared theta. Again, cosine squared minus sine squared is I think cosine of 2 theta. So you could do some factoring, like factor out a -2, and you would have that version. But I'm just saying, okay, I have a cosine theta and a cosine squared, so I should get rid of the sine squared. I prefer to do that because then it usually factors. So instead of sine squared, 1 minus cosine squared theta. Okay. So what are we going to have here? We're going to have -2 cosine squared and another -2 cosine squared. So -4 cosine squared theta plus 2 cosine theta plus 2. And how about we take a GCF of -2 out so that it becomes +2 cosine squared theta minus cosine theta minus 1. That's easier for me to factor. 2 cosine theta, 1, 1, make that one minus, make that one plus. Set each of these equal to 0. Finally, get our thetas. All right, when is cosine theta equal to -1/2? Well, cosine's equal to 1/2. The reference angle is pi/3, but we need where in the quadrants where cosine's negative. So we need the 2 pi/3 and 4 pi/3, quadrants 2 and 3. And then when is cosine equal to 1? +1, that's happening at 0, and 2 pi, but I don't really need the 2 pi. All right, so the question is, where do we have horizontal tangents? Remember, we're plugging into r equals 2 times 1 minus cosine theta. Okay, so horizontal tangents when dy dx is equal to 0. So at 0, 2 pi/3 and 4 pi/3, but x prime can't be 0 either, so 0 is out of the question. All right, so we have 2 pi/3 and 4 pi/3. And what is r at those two angles? So if you plug in 2 pi/3, we have 1 minus cosine of 2 pi/3. So cosine of 2 pi/3 is -1/2, right? 1 minus -1/2 is 3/2, times 2 is 3. You can write that all down. I'm just kind of running out of room. 4 pi/3 again that's when cosine's -1/2. So we're going to get a value of 3 again. So those are 2 points for horizontal tangents. And then where do we have vertical tangents? Anywhere where dx dt is equal to 0 and dy dt is not. So at pi, they both don't share that. Pi/3 is okay and 5 pi/3 is okay because those aren't our two angles here. So we've got a pi, we've got a pi/3, and we have a 5 pi/3. And then we just plug each of those angles into r. So pi. 1 minus -1 is 2. 2 times 2 is 4. Pi/3. 1 minus 1/2 is 1/2. Times 2 is 1. 5 pi/3, cosine's positive. So we're going to get the same thing. 1 minus 1/2 times 2 is 1. Okay, those take a lot of work, but they are kind of systematic, which is nice. Find the equations of tangent lines for r equals 2 cosine of 3 theta at the pole. So at the pole, find the equations of the tangent line. So at the pole is 0 for r, and then theta can really be anything. So that's something to keep in mind. For this, I do need dy dx put together. Okay, so the first thing I should find, I'm using this formula up here. I'm using this guy that I'm going to memorize eventually. First thing I need for this formula, excuse me, is r prime. So let's write that over here. R prime would be, let's see, 2 times negative sine 3 theta, and then chain rule puts an extra 3 out there. So negative 6 sine of 3 theta. Now the formula is r prime sine theta plus r cosine theta over r prime cosine theta minus r sine theta. Okay, so r prime times sine is going to be negative 6 sine 3 theta just times sine theta. So that's not a sine squared or anything because their angles are different. Plus r is 2 cosine 3 theta cosine theta. Denominator, r prime times cosine theta. Negative 6 sine 3 theta times cosine theta minus r is 2 cosine 3 theta times sine theta. Now we can have any angle we want at the pole, but r is equal to 0. And so there are a couple of things I want to note before I figure this out. I need an equation for a tangent line. So the point can be anything because the point is 0 at any angle. But the slope needs to be, the slope when I plug in some value of theta for which the pole becomes 0. So I need a theta is what I'm trying to get at here. There's one thing that's going to make our lives easier. Instead of plugging into all of this mess, one thing to note, remember, r is 0. So anywhere we had an r in this equation, so like here, we're really going to get 0 times cosine theta. Same thing here, 0 times sine theta. So this is unique just because we're finding things at the pole. This wouldn't always be true, but I can actually eliminate this and pare this thing down a ton. This is negative sine of 3 theta sine theta plus 0, right? Over negative sine 3 theta cosine theta plus 0 again, or minus 0 technically. And then now that I have this as a single fraction and it's all multiplication in here, all that goes away. dy dx is simply, at the pole, is simply tangent theta. That's amazing. That's way easier to plug into than all of this. Okay. So what theta are we supposed to plug in here? Well, we know that 0 is supposed to equal to cosine of 3 theta. So let's figure out an angle for which that's true. So when is cosine equal to 0? When 3 theta equals pi over 2 or 3 pi over 2. And so divide by 3, pi over 6, or divide by 3, pi over 2. And so I can figure out, it says equations, so I have two angles here. So I can figure out, all right, what's dy dx evaluated at theta equals pi over 6? What's the tangent of pi over 6? Opposite's 1, adjacent's radical 3. It's radical 3 over 3. And what is the tangent of pi over 2? Undefined. That must be a vertical tangent. Okay, so what are our equations? Well, if we have a vertical line, then we need an equation for a tangent line that would just be x equals. So what does x equal? X equals, I'm going to write a note, vertical tangent. X equals r times cosine theta. X equals 2 cosine 3 theta times cosine theta. And at pi over 2, x equals 2 times 3 pi over cosine of 3 pi over 2 is 0. Cosine of pi over 2 is 0. So just x equals 0 is a vertical tangent. And then at radical 3 over 3, I'm going to do this up here because, again, out of room. Since that's not a vertical or a horizontal line, I need an xy coordinate for radical 3 over 3. So what's x of radical 3 over 3? I'm going to use my work over here. 2 times the cosine of pi over, I'm sorry, what's x of, not radical 3 over 3, what's x of pi over 6? Excuse me. It's 2 times the cosine of, well, 3 pi over 6 is pi over 2. So that's 0 right there, right? Cosine of pi over 6. So the x coordinate's 0. And then what's y of pi over 6? y of pi over 6 is 2 cosine of pi over 2 and sine times sine of pi over 6. But again, cosine of pi over 2 is 0. So we have a point 0, 0. Y minus 0 equals radical 3 over 3 times x minus 0. Basically, y equals radical 3 over 3x. So that line is a tangent line equation as well. Okay, this was a long one. Our homework for tonight is homework number 33, which takes you through a little bit of graphing, but also some of this tangent, horizontal and vertical tangent points. That's good to practice. And then there is a graphing worksheet where you can get extra practice graphing as well. So just 4 quick problems. This grid paper, this one's pi over 4. That's pi over 6. This would be pi over 12. We don't really need that one. This one's pi over 3. We don't need that point either. So just keep that in mind. All right, that's it.